Hi there. In this recording, we are going to talk about the Doppler effect. Let's start by introducing Billy and Timmy. Billy and Timmy are going to be playing balls. Billy will be tossing golf balls towards Timmy, who's going to catch them. We'll have several scenarios that we are going to use. The first scenario, Billy and Timmy are about 20 meters apart. They are both standing still at their positions. Billy is to toss one golf ball every minute towards Timmy. Timmy is expected to catch all balls. So that's what's going to happen. Every minute, Billy tosses a ball, Timmy catches it. The question is, what is the frequency with which Billy tosses balls? Frequency, remember the meaning of the word. So how frequent are Billy's tosses? That's what the question means. Of course, since he's tossing a ball every minute, the frequency is 1 per minute. The next question then is, what is the frequency with which Timmy receives balls? Now, since Billy tosses a ball every minute towards Timmy, and since Timmy receives all balls, so Timmy is going to be receiving a ball every minute, or the frequency with which Timmy receives balls is going to be 1 per minute. Okay, let's look at the second scenario. Notice here, Billy and his bucket are standing on a skateboard that is moving at a constant speed towards Timmy. So we have a situation like the previous situation, except that Billy in this case, while tossing balls, is going to be moving at a constant speed towards Timmy. Again, he's going to be tossing one golf ball every minute, and Timmy is expected to catch all the balls. So this is what happens. Now, after 1 minute, when he's further ahead, he's going to toss another ball. I'm not going to be able to show you that here, but let's go back to the first toss. So as he tosses the ball, he's also moving forward. The question now again, what is the frequency with which Billy tosses balls? Obviously, it's still 1 per minute since he tosses balls every minute. So the frequency with which Billy tosses golf balls is 1 per minute. The second question is, what is the frequency with which Timmy receives balls? Now, however, before you answer this, remember that 1 minute after tossing the first ball, Billy is actually closer to Timmy. So when he's ready to toss the second ball, he's closer to Timmy than he was a minute ago. So what does that mean? That means the second ball will move a shorter distance before reaching Timmy. The second ball does not have to travel as far. The first ball had to travel this much. The second ball is going to travel only this much. Which means that the second ball, if he's tossing balls with the same speed, the second ball is going to take less time to reach Timmy. So what does that mean? That means that Timmy is going to receive balls more frequently than 1 per minute. Since subsequent balls are taking less time to arrive to Timmy, so he's receiving more golf balls per minute than when Billy was standing still. So the conclusion is, even though Billy tosses the ball at the same frequency of 1 per minute, Timmy receives the balls at a higher frequency of 1 per minute. The question is then, does this happen only when Billy is moving towards Timmy? No, we should expect the same conclusion if it is actually Timmy that's on the skateboard and getting closer to Billy. Because in that case as well, after 1 minute, Timmy is going to be closer to Billy, and the golf ball is going to take lesser time to arrive to Timmy. The same also would happen if both of them are moving towards each other. Both of them are on golf boards and moving towards each other. All these three scenarios, Billy moving towards Timmy, Timmy moving towards Billy, or both moving towards each other, would result on Timmy measuring a higher frequency or catching the balls at a higher frequency than 1 per minute. One might ask, what would happen if Billy was moving away from Timmy instead of moving closer to Timmy? Which means 1 minute after tossing the first ball, Billy is going to be further away from Timmy. Which means the second ball and subsequent balls are going to take longer time to reach Timmy. This obviously means that Timmy is going to be receiving the balls less frequently than 1 per minute, or he's going to measure a lower frequency than the launching frequency of 1 per minute that Billy is using for tossing the balls. Now, of course, we should get a similar result whether Billy is moving away from Timmy, Timmy is moving away from Billy while Billy is standing still, or both of them are moving away from each other. The key is the distance separating them is increasing as subsequent balls are being tossed. So in conclusion, whenever Billy and Timmy move relative to each other, that's whether they are moving closer to each other or away from each other, whether one of them only is moving or both of them are moving. Whenever they move relative to each other, the frequency that they measure of the exchanged balls would be different. Billy is going to always measure the frequency with which he tosses the balls, which is in this case 1 per minute. Timmy is going to measure either smaller frequencies or larger frequencies. Timmy would measure a higher frequency when they actually move towards each other, and a lower frequency when they move away from each other. Now, the speed with which Billy and Timmy move relative to each other is what's going to determine the frequency recorded by Timmy. For example, if Billy is moving towards Timmy with a certain speed, we said Timmy is going to measure the balls as arriving him more frequently than 1 per minute. Now, if Billy is going to move at a faster speed, it's going to take even lesser time for the balls to reach Timmy, so he's going to measure them even more frequently. So the speed with which Billy and Timmy are moving relative to each other is what's going to determine the frequency recorded by Timmy. However, the speed with which Billy tosses the golf balls has no effect on the frequency recorded by Timmy. As long as he's going to toss all balls with the same speed, it's going to have no effect. And this effect that we just described, we call it the Doppler effect. However, we really deal with the Doppler effect only when we talk about waves, not tossing balls. So the introduction that we did, the scenarios that we discussed, were to introduce us to the concept. So the Doppler effect is a wave property. It is experienced by all waves, no matter whether they are water waves, sound waves, electromagnetic waves, visible light waves, part of the electromagnetic spectrum, whatever type of waves they are, they can experience the Doppler effect. And the key is the source that's producing the waves is moving relative to whatever is detecting the waves, the receiver. In particular, We often talk of the Doppler effect for sound waves and for electromagnetic waves. Let's start talking about the Doppler effect for sound waves. In this case, we are relying on a simulation where we have an ambulance that can move towards a receiver here, a cyclist. So the ambulance has the same role as Billy, and the cyclist has the same role as Timmy. The ambulance is going to have a siren that's going to produce sound at a particular frequency. So what's the sound? What does it mean? Okay, the ambulance is going to have a sort of a speaker that's going to compress air molecules back and forth. As the membrane of the speaker moves back and forth, it's going to compress the air molecules and then expand them, compress them and expand them. And that vibration of the air molecules is what's going to travel through the air to reach the ears of the cyclist. So now these compressions, these vibrations that are traveling through the air is the equivalent of the golf balls that we discussed before. With a small distinction, please. It is the vibration that we are discussing. It's not the molecules of the air. We don't have a molecule of air that's going to go all the way from the speaker to the ear. It's the vibration of the molecules that's going to travel. So the molecules here are going to vibrate in place here at this position. But because of their vibrations, they are going to induce the molecules of air that are next to them to vibrate, etc. And that's what's going to allow the vibration to propagate till it reaches the ear of the cyclist. Okay, so here we have it. In this first case, what happens if neither ambulance or cyclist move? Okay, so we'll start it. Okay, you notice here, as the waves are being produced, we are drawing here essentially the compression waves, the front of the wave we are showing it. And whenever it's received by the cyclist, we had for a little while, the cyclist turn red to show that he received a front. Now, notice here that all these circles that were produced of the front of the waves, they are centered around where they are produced in the ambulance. And they are equidistant. They are the same distance apart. Same distance apart. We don't see the back here, but it's the same distance apart in all directions. Now, if we listen to the sound produced by the ambulance, this is what we get. Okay, if we listen to the sound heard by Timmy, this is what we get. And you notice here, both sounds were at the same pitch. They sound identical. And that's very much like Billy measuring 1 toss per minute, while Timmy measuring 1 reception per minute. Same frequency, so here we have the same frequency sounds. Now, what if the ambulance is getting closer to the cyclist? Okay, now here notice the back and the front of the ambulance. You notice here in the front, the compressions are closer to each other. So the cyclist is going to perceive them more frequently than the way they were produced by the ambulance. The way they were produced by the ambulance is what we saw in the previous slides. Okay, now the way they were produced by the ambulance, this is the way they sound. Now the way they are perceived by the cyclist, this is the way they sound. You notice that it is at a higher pitch. Okay, let me repeat just in case. you notice that it was a higher pitch. Higher pitch meaning it's a higher frequency. And it's a higher frequency because they are closer apart here as they arrive to him. That's very much like when Billy was moving closer to Timmy. As he was moving closer to Timmy, subsequent balls were taking lesser time to reach Timmy. So in this case, subsequent compression waves are taking lesser time to reach the cyclist. One might ask, what would happen if the ambulance is moving towards the cyclist even faster? Okay, so we test that. Okay, so this is moving faster. Okay, you notice that the compression fronts are even closer to each other. So that tells us the cyclist is going to measure an even higher frequency. So the speed of the ambulance, like the speed of Billy, or the speed they move relative to each other, is what's going to determine the frequency as measured by the cyclist. Now let's see how it sounds. This is the frequency from the ambulance. And this is the frequency perceived. And you notice that it is a higher pitch. Okay. Now, of course, what about if the source is moving away from the receiver? What about if the ambulance is moving away from the cyclist? Okay, let's play that. Okay, you notice in this case, the receiver, the cyclist, is actually getting fronts that are further apart, getting compressions that are further apart. So the cyclist is going to be measuring a lower frequency. And in this case, instead of hearing this sound as produced from the ambulance, it's going to hear this sound, lower pitch. Okay. Now, of course, if the ambulance is moving faster, like here, the separation between the fronts is even more, telling us that the cyclist is going to measure an even lower frequency. And if this is again the sound of the source, this is the sound heard by the cyclist. Much lower pitch. Okay. Okay, one thing that's important, it is not loudness that is different. It is the pitch. Okay, let's listen to this to see the difference in loudness. Loud, less loud. See, it's the same pitch, but it's less loud. As compared to this, and this. You see, the pitch here is quite different. Now, because of the way we hear things, sometimes it's going to sound louder, but that's just an artifact of the way we hear, or an artifact with the way the speakers that we use in our computers work. It's not the Doppler effect. The Doppler effect is focused only on the pitch, the change in frequency, not on the loudness. So in conclusion, like when tossing balls, the receiver measures a different frequency than the source. The receiver, in this case, the cyclist. The source is the ambulance siren. The difference in frequency depends on how the source and receiver move relative to each other. Now, if they are moving closer to each other, the receiver is going to perceive a higher frequency or higher pitch. If the source and receiver are moving away from each other, the receiver is going to perceive a lower pitch, a lower frequency. Again, for sound, the frequency is perceived as pitch. One might ask, what about light? Okay, like sound, light is associated with frequencies. For example, here I have frequencies in terahertz. Now, along with the frequencies, I have the wavelengths here in nanometers. And then in this table, we have the color that corresponds to the various frequencies. For example, here we have red. That's frequencies between 400 and 484 terahertz. That's what we perceive as red. Green, something between 526 and 606, is normally perceived as green, and so on. So this is the visible spectrum of light and their corresponding frequencies. If our source is producing light at a particular color, let's say in the green range, and then that source is moving closer to a receiver, something that's going to detect that light, an eye or a camera. If it is moving closer to the receiver, what we are going to perceive is a higher frequency. A higher frequency means what? Something here, let's say if we started with 606 green, what we will get is something above 606. It's going to be more towards the blue. If it is a 606 green and the source is actually moving away from the receiver instead of moving closer to the receiver, we are going to perceive a lower frequency. A lower frequency might be 526. 526 is still green, but it's a lower frequency. If the speed is even higher, it's moving away with a higher speed, we might go down to 525. Then it's yellow. Now, what we call that, I have the arrows here to represent what we usually refer to it. If this is the frequency with which the source is emitting light, if the source is moving towards the receiver, we say we have a blue shift, an increase in frequency. We refer to that as a blue shift. It does not mean that the light we are going to see is going to be really blue, but it means we have an increase in frequency. It is moving towards the blue. And if we perceive a lower frequency, because the source and the receiver are moving apart, we say we have a red shift. Like here, for example, we don't really see red, but the frequency is moving towards the red frequencies. We call that a red shift. The same thing that happens with sound happens with light. So if the source and the receiver move towards each other, then the frequency is going to increase. An increase in frequency in terms of light corresponds to a color change in terms of visible light. That's why we use the term of blue shift or red shift. Now, red shift, we get it when the source, whatever is emitting the light, and the receiver are moving away from each other. Okay, red shift, decreased frequency, blue shift, increased frequency. That's what we have with visible light. What about wavelengths other than visible light? Other electromagnetic waves that are not visible. For example, the waves that are used in Doppler Radar, microwave frequencies. For example, here we have the list of microwave frequencies. They go from 1 gigahertz to about 110 gigahertz, depending on the bands that we call. Now, Doppler Radar, we use it to measure the speed of air masses to predict weather patterns. Very much like for sound, whenever the source and the receiver are moving relative to each other, we are going to measure different frequencies. The change in frequency is going to depend on the speed. In this case, we have a table that shows only the change in frequencies, not the actual new frequency. For example, if the speed of the air masses is 1 meter per second, if we are using a source with 9.37 gigahertz, so we have this slight change in frequency, 62.5 hertz. However, if the speed is 50 meters per second, you see it's a much bigger change in frequency. So this is the change, 9.37, plus we need to add this change. And we have the changes for different types of sources that can be used. Doppler Radar is used for measuring the speeds of cars as well in speed enforcement. For example, if the patrolman uses a radar frequency that's going to have this frequency, and the car is moving towards the highway patrolman, then the reflected frequency, or the frequency as measured by the car, is going to be a higher frequency. Now, if the car is moving away from the patrolman, the frequency measured by the car, which is also reflected and can be measured by the highway patrolman, is going to be a lower frequency. So very much like for sound, if the source, the highway patrolman that's standing still, and the receiver, the car, if they are moving closer to each other, we are going to get a higher frequency. Away from each other, we are going to have a lower frequency. And we interpret that the same way as we interpret visible light, even though we don't see it. So a higher frequency is a blue shift, a lower frequency is a red shift. Here, the blue and red are not really representing colors, they are more representing a shift in frequencies. In conclusion, now for all types of waves, when the source of a wave moves relative to the receiver measures a different frequency than the frequency produced by the source. That's the Doppler effect. The frequency is higher when the source and receiver approach each other, and lower when they move apart. Also, the shift in frequency depends only on how fast the source and receiver move relative to each other. That's the only factor that affects that change in frequency.